This is the main DTA algorithmic structure, and it represents the following three concepts: simulation, shortest path, and path updates. The simulation can be run for only the peak hours of a day, or for the whole 24 hours, and is a process to carry out the representation of time-varying traffic dynamics, given that each vehicle follows a predetermined route. At the end of the simulation, key information is stored for future use. Arrays store the time-varying travel time and travel delay, as well as other variables. Taking this information, we can solve for a time-dependent shortest path. The path adjustment phase allows for various users to adjust their routes if they are too inefficient, and lets them shift their paths to be more close to the time-dependent shortest path. Only a certain number of vehicles will be selecting the newly found time-dependent paths. The whole process can be described as a sort of day-to-day learning. At the start of each day, the simulation is run, and each vehicle has their own path. The simulation loads in each vehicle with their individual paths and carries out the representation of traffic dynamics and congestion over the period of interest. At the end of the simulation, the key data is stored for use by future processes. This information includes travel time and intersection delays, and is input to calculate the time-dependent shortest path. These shortest paths are given to those drivers who had the most travel delay and longer travel times than expected. The path adjustment process is the assignment portion of the algorithm, where it is determined which vehicles will be taking the time-dependent shortest path. If few vehicles are given these new paths, then convergence has been achieved. If too many are taking the new path, then that means that time-dependent shortest path may get overloaded in the next iteration. Thus, the decision-making process for selecting which vehicles are assigned new paths is critical in how fast the algorithm will converge. After all this, the simulation is run again to evaluate the path updates. This whole process is then repeated until convergence is reached. The convergence check is based on the gap function before the next set of path updates and decides whether or not to run the next iteration.